Singularity, where space, time, and reality break down. Right now, somewhere in this universe, roughly 26,000 light years from where you are sitting, there is a point. Not a star, not a planet, not any physical object you could touch or see or measure in any conventional sense. It is a point where the density of matter is calculated to be infinite, where the curvature of space-time folds so violently upon itself that the very fabric of reality, as we understand it, simply stops making sense, where the temperature is listed in our equations as infinite, where the volume reads as zero, where every law of physics that has ever been tested, confirmed, and relied upon goes silent. This point sits at the heart of Sagittarius A star, the supermassive black hole anchoring our entire Milky Way galaxy. And according to our best theory of gravity, that point is not optional. It is not a quirk. It is not a flaw in the math. It is, according to general relativity, an inevitability. We call it a singularity. And here is what makes it one of the most disturbing ideas in all of science. A singularity is not simply a place where things are very extreme. It is a place where the theory that predicts it also confesses that it can no longer describe what is happening there. General relativity, Einstein's majestic framework for understanding how mass and energy curve the geometry of space and time, predicts the existence of singularities. And then it breaks down at their doorstep. It is a theory brilliant enough to foresee its own failure, honest enough to announce it, and yet unable to offer a replacement. Singularities sit at the center of every black hole in the cosmos. There may be billions of them scattered across the observable universe. And if you run the clock backward to the very beginning, to the moment the universe itself was born, you arrive at another one. The initial singularity, the Big Bang, a state of infinite density and temperature from which everything you have ever known, every atom in your body, every photon of light that has ever struck your eye, somehow emerged. These are the places where space, time, and reality break down. And understanding them, or understanding why we cannot understand them, is one of the deepest pursuits in modern physics. What are singularities, really? Are they physical things that exist in the universe, or just warning signs that our theories need updating? What would happen if you fell toward one? Could we ever see one directly? And is it possible that the most advanced ideas in physics, the ones working at the ragged frontier of human knowledge, might erase singularities from the cosmos entirely? Consider the sheer strangeness of the claim. We live in a universe governed by laws. Every particle interacts according to precise rules. Every force follows equations that have been tested billions of times. The conservation of energy, the conservation of momentum, the conservation of electric charge, these principles never fail. They hold in laboratories and in galaxies, in the hearts of stars, and in the spaces between atoms. They are, as far as anyone has ever been able to determine, absolutely universal. And yet general relativity tells us there are places where all of this machinery stops working. Not because the conditions are merely extreme, but because the mathematics that describe our reality reach a point where they produce no answer at all. The theory does not say the answer is very large. It does not say the answer is beyond our current ability to calculate. It says, in effect, there is no answer. The equations themselves go silent. And the unsettling question is whether that silence is a property of the theory or a property of the universe. To answer these questions, we need to go on a journey through the mathematics of curved space-time, through the lives of the extraordinary minds who discovered singularities lurking in Einstein's equations, through the interiors of black holes where gravity becomes monstrous, and ultimately to the bleeding edge of theoretical physics, where quantum mechanics and gravity collide in ways we are only beginning to fathom. This is the story of singularities, the places where our understanding ends and our deepest questions begin. But before we dive into the mathematics and the physics, take a moment to appreciate just how strange the situation is. In every other area of science, when a theory produces an absurd result, we discard the theory or modify it. We do not take the absurd result at face value. When 19th century physics predicted that a heated object should emit infinite energy at short wavelengths, an absurdity known as the ultraviolet catastrophe, physicists did not conclude that the universe actually produces infinite energy. They concluded that the theory was wrong, and the resolution, quantum mechanics, launched an entirely new era of physics. When classical electromagnetism predicted that an accelerating electron would spiral into the nucleus of an atom in a fraction of a second, physicists did not conclude that atoms are unstable. They concluded that a deeper theory was needed, and again quantum mechanics provided the answer. Singularities in general relativity are different. They are not easily dismissed, because the theory that predicts them has been confirmed with extraordinary precision in every other domain. General relativity correctly predicts the precession of Mercury's orbit to within 1 part in 10 million. It correctly predicts the bending of starlight by the sun. It correctly predicts the existence and behavior of gravitational waves, which were directly detected for the first time in 2015, a full century after Einstein's theory predicted them. It correctly predicts the structure of the cosmic microwave background radiation. It correctly predicts the dynamics of binary pulsars. There is no domain of gravity where general relativity has been tested and found wanting. And yet this supremely successful theory, this crown jewel of human intellectual achievement, insists that singularities are real, that matter can collapse to infinite density, that space-time can curve to infinite curvature, that the orderly progression of cause and effect can come to an abrupt and unexplainable end. Either the universe really does contain these impossible points, or there is some deeper layer of reality, some more complete theory that we have not yet discovered. Either way, singularities are telling us something important, something fundamental, something we cannot afford to ignore. When mathematics misbehaves, to understand what a singularity is, you first need to understand something about how physics works. Physics is, at its core, a language of equations. We observe the world, we notice patterns, and we write down mathematical relationships that capture those patterns with extraordinary precision. Newton's law of gravity tells you how strongly two masses attract each other depending on their distance. Maxwell's equations tell you how electric and magnetic fields dance together to produce light. Einstein's field equations of general relativity tell you how the presence of matter and energy sculpts the geometry of space-time. These equations are our maps of reality. And like any map, they are only useful if they provide sensible answers. If you plug numbers into an equation and get a reasonable result, a finite number, a meaningful prediction, then the map is working. But sometimes, when you push an equation into extreme territory, it gives you an answer that is not reasonable at all. It gives you infinity. In mathematics, a singularity is precisely this, a point where a function or equation produces an infinite or undefined result. They are surprisingly common. Consider the simple expression 1 divided by x. As x gets smaller and smaller, approaching 0, the value shoots upward without limit. At x equals 0, the expression is undefined. That is a mathematical singularity. Now, in many areas of physics, singularities pop up all the time, and they are usually not cause for panic. They are typically signs that the model you are using has been stretched beyond its intended range. The equations describing a fluid, for example, might predict infinite pressure under certain conditions, but that just means the fluid model breaks down, not that the universe actually produces infinite pressure at that point. You swap in a better model, one that accounts for the molecular structure of the fluid, and the singularity vanishes. Problem solved. But gravitational singularities are different. They are predicted by general relativity, our best and most thoroughly tested theory of gravity, the theory that has been confirmed by every experiment thrown at it for over a century. And unlike the singularities in fluid dynamics or electromagnetism, gravitational singularities are not easily patched. They seem to be woven into the very structure of the theory. When you follow the equations of general relativity to their logical conclusion in certain physically realistic situations, like the collapse of a massive star, they stubbornly insist on producing infinities. And nobody has been able to make those infinities disappear within the framework of the theory itself. There are several types of gravitational singularities that physicists have identified, and each has its own character. The most famous is the curvature singularity. This is the kind that lurks at the center of a black hole. Here, the curvature of spacetime, which is general relativity's way of describing the strength of gravity, grows without bound. It becomes infinite. The density of any matter that has fallen and becomes infinite. The tidal forces, the differential gravitational pull that would stretch and compress any object, become infinite. There is no coordinate system, no mathematical trick, no change of perspective that can remove this infinity. It is what physicists call a true singularity, as opposed to a coordinate singularity, which is a mathematical artifact that disappears when you describe the same situation in different coordinates. The event horizon of a black hole, for instance, was once mistakenly thought to be a singularity. In the original coordinate system used by Carl Schwarzschild, certain quantities appeared to blow up at the event horizon. But later work by physicists like Georges Lemaitre, Arthur Eddington, David Finkelstein, and Martin Kruskal showed that this was just a coordinate singularity. Choose a different set of coordinates, and the event horizon becomes perfectly well-behaved. Spacetime there is smooth. An astronaut falling through would notice nothing unusual at the moment of crossing. But the singularity at the center? That one stays. No matter what coordinates you use, no matter how clever your mathematical approach, the curvature invariants, the quantities that measure the intrinsic geometry of spacetime and are the same in every coordinate system, diverge. They become infinite. And this is deeply unsettling, because in physics, infinity is almost always a sign that something has gone wrong with your theory. There are also conical singularities, which are geometrically simpler but no less strange. Imagine taking a flat sheet of paper, cutting out a wedge, and then gluing the edges together. You get a cone. The tip of the cone is a point where the geometry is not smooth, even though the paper is perfectly flat everywhere else. In spacetime, a conical singularity would look something like a cosmic string, a hypothetical one-dimensional defect in the fabric of space that may have formed in the early universe. At the location of the string, spacetime has a sharp point, a place where geometry itself is not well defined. And then there are the singularities that physicists worry about most, the ones that are, or are not, hidden behind event horizons. A singularity tucked safely inside a black hole, invisible to the outside universe, is troubling enough. But a naked singularity, one that is visible to distant observers, one that can send signals and influences outward, would be far worse. It would represent a place where the laws of physics break down in full view of the cosmos, where the universe itself has a gaping wound that nothing in our current understanding can close. Whether naked singularities exist in nature is one of the most important unresolved questions in gravitational physics, and we will return to it later. For now, the essential point is this: a singularity is not just a place where things get very extreme. It is a place where the equations that describe reality produce results that are literally meaningless. Infinite density, infinite curvature, zero volume. These are not physical descriptions of something that exists. They are the theory's way of throwing up its hands and saying, I cannot help you here. And the question that has consumed theoretical physicists for more than a century is whether singularities are real features of the universe, actual places where physics ceases to function, or whether they are just symptoms of our ignorance, signals that general relativity needs to be replaced by a deeper, more complete theory that does not break down when gravity becomes extreme. That question began with a dying man in the trenches of World War I. But before we meet him, it is worth pausing to appreciate what Einstein had created and why finding solutions to his equations was so remarkably difficult. Newton's law of gravity, the equation that had reigned for over 2 centuries, was comparatively simple. It described gravity as a force between two masses, proportional to the product of their masses and inversely proportional to the square of the distance between them. A bright high school student could use Newton's equation to calculate the gravitational pull between the Earth and the Moon with nothing more than a pencil and paper. Einstein's equations were in a completely different league. Instead of a single equation relating force to mass and distance, general relativity consists of 10 coupled, nonlinear partial differential equations that describe how the curvature of a 4-dimensional spacetime manifold is related to the distribution of matter and energy within it. The equations are so intertwined, so deeply entangled with each other, that changing the matter distribution in one place affects the curvature everywhere, and that changed curvature in turn affects the motion of the matter, which changes the curvature again, in a continuous feedback loop. They are among the most difficult equations in all of physics, and finding exact solutions, meaning solutions that are not approximate but mathematically precise, was a challenge that Einstein himself was not sure could be met. He had managed to wring out approximate solutions, enough to calculate the anomalous precession of Mercury's orbit, which had been a nagging mystery for decades, and to predict that light from a distant star would be bent by a specific angle as it passed near the Sun. Both predictions would be confirmed by observation, cementing general relativity as one of the most successful theories in the history of science. But exact solutions? Those seem like they might be forever out of reach. The man who found the first one. In November of 1915, Albert Einstein stood before the Prussian Academy of Sciences in Berlin and presented the culmination of a decade of grueling intellectual labor. His general theory of relativity was finally complete. It described gravity not as a force pulling objects together, as Newton had imagined, but as the curvature of spacetime itself. Matter tells spacetime how to curve. Spacetime tells matter how to move. It was breathtaking in its elegance and punishing in its mathematical complexity. Einstein's field equations formed a set of 10 interconnected, nonlinear partial differential equations in 4 dimensions, and even Einstein himself had struggled to extract solutions from them. He had managed to produce approximate solutions, enough to make predictions about the orbit of Mercury and the bending of starlight by the Sun, predictions that would soon be spectacularly confirmed. But finding exact solutions, precise mathematical descriptions of how spacetime curves around specific arrangements of matter, seemed like it might be impossible for all but the simplest cases. Then, within weeks of the theory's publication, a letter arrived from the Russian front. Karl Schwarzschild was a remarkable figure. Born in Frankfurt in 1873 into a prosperous Jewish family, he had shown a precocious talent for mathematics and astronomy from childhood. By the age of 16, he had published 2 papers on the orbits of binary stars. He went on to become director of the Astrophysical Observatory in Potsdam, one of the most prestigious positions in European science. He was brilliant, hardworking, and by all accounts possessed of a warm and generous personality. When World War I erupted in 1914, Schwarzschild was in his early 40s. Despite his age and his position, he volunteered for the German army out of patriotism. He served as an artillery officer, applying his mathematical gifts to the calculation of ballistic trajectories. He saw action on both the Western and Eastern fronts. And it was while stationed on the Russian front, amid the mud and the cold and the constant threat of shellfire, that he received Einstein's newly published papers on general relativity. What happened next was extraordinary. Schwarzschild, working in the spare hours between his military duties, found the first exact solution to Einstein's field equations. He considered the simplest possible scenario, a single, spherical, non-rotating mass sitting alone in an otherwise empty universe. Think of the sun, but idealized, a perfect sphere with no spin. He fed this into the machinery of general relativity, and out came a complete, exact description of how space-time curves around such an object. It was elegant, it was beautiful, and it contained something deeply strange. Schwarzschild sent his solution to Einstein in a letter dated December 22, 1915. In it, he wrote with characteristic humor, "As you see, the war is kindly disposed toward me, allowing me, despite fierce gunfire at a decidedly terrestrial distance, to take this walk into this your land of ideas." Einstein was reportedly delighted. He had not expected that anyone could find an exact solution so quickly or so simply. But Schwarzschild's solution had 2 points where the mathematics misbehaved. 2 places where certain quantities in the equations became infinite. One was at a specific radius from the center of the mass, a distance that would later become known as the Schwarzschild radius. The other was at the center itself, at a distance of 0. For decades, physicists debated the nature of these 2 singularities. Were they real, physical features of space-time, or were they artifacts of the particular coordinate system Schwarzschild had used? The singularity at the Schwarzschild radius was resolved first. Over the following years, a series of physicists showed that it was a coordinate singularity, similar to the mathematical infinity you encounter at the North Pole if you try to use longitude as a coordinate. Choose a better set of coordinates, and the Schwarzschild radius becomes a perfectly smooth region of space-time. It is still special. It is the event horizon, the boundary of no return beyond which nothing can escape the gravitational pull of the mass. But it is not a place where physics breaks down. An astronaut passing through would not even notice the moment of crossing, at least not from any local measurement. The singularity at the center, however, was a different matter entirely. No change of coordinates could remove it. The curvature of space-time, as measured by quantities that are the same in every coordinate system, diverged to infinity. This was a true singularity, and it was the first one ever discovered in the equations of general relativity. Schwarzschild himself did not live to see the decades of debate his solution would spark. While on the Russian front, he contracted pemphigus, a rare and agonizing autoimmune disease that causes the body's immune system to attack the skin, producing painful blisters that can cover the entire body. The disease was little understood at the time, and there was no effective treatment. He was invalided home in March 1916 and died just 2 months later, on May 11th, at the age of 42. His colleagues mourned the loss deeply. Einstein himself wrote in Schwarzschild's obituary that his death was a great loss for science, which had so much more to expect from him. In an extraordinary twist of historical irony, the name Schwarzschild translates from German as Black Shield. The man who first mapped the geometry of what we now call a black hole carried its description in his very name. It is the kind of coincidence that would seem too neat for fiction, yet it is entirely real. His solution would sit in the physics journals for years, a mathematical curiosity that most physicists, including Einstein himself, believed had no physical relevance. The idea that a real object could be compressed below its Schwarzschild radius, triggering an unstoppable gravitational collapse to a singularity, seemed absurd. After all, What force in nature could crush matter down to zero volume? What process could produce truly infinite density? Surely something would step in to prevent it. Surely some force, some pressure, some mechanism would halt the collapse before things got that extreme. The Schwarzschild radius itself is remarkably small for objects of ordinary density. For our Sun, it is about 3 kilometers. For the Earth, it is less than 9 millimeters, roughly the size of a marble. To compress the Sun below its Schwarzschild radius, you would have to squeeze all of its mass, some 2 times 10 to the 30 kilograms, into a sphere smaller than a modest hilltop. The density at that point would be roughly 10 to the 19 kilograms per cubic meter, far beyond anything encountered in ordinary experience, but, as it would turn out, not beyond what the universe could achieve. And for a while, it seemed like the skeptics might be right. The discovery that quantum mechanics provided new sources of pressure, electron degeneracy pressure and neutron degeneracy pressure, seemed to offer a natural barrier against total gravitational collapse. Matter could be dense, incredibly dense, but it would always find a floor to rest upon. Gravity could be strong, overpoweringly strong, but there would always be a counterforce to push back. The story of how that comfortable assumption was shattered begins with a 20-year-old prodigy on a ship from India. The reluctant acceptance. The decades following Schwarzschild's discovery were not kind to singularities. Most physicists treated them as mathematical embarrassments, artifacts of unrealistic assumptions that would vanish once you accounted for the messy complications of real matter. The singularity in Schwarzschild's solution assumed a perfectly spherical, non-rotating mass. Real stars spin. Real matter has pressure. Real collapse is not perfectly symmetric. Surely these factors would prevent any actual singularity from forming. Einstein himself was the most prominent skeptic. In a 1939 paper, he argued explicitly that singularities could not form in nature. He constructed a model of a cluster of particles orbiting each other under their mutual gravity and showed that, in his model, the particles could never be compressed below the Schwarzschild radius. He concluded that the singularity predicted by Schwarzschild's solution was a mathematical idealization with no counterpart in the real universe. But even as Einstein was publishing his rejection of singularities, a young physicist at the University of California, Berkeley was arriving at the exact opposite conclusion. Robert Oppenheimer is best remembered today as the father of the atomic bomb, the haunted genius who led the Manhattan Project and then spent the rest of his life grappling with the moral weight of what he had created. But before the war consumed his career, Oppenheimer was a gifted theoretical physicist with a deep interest in stellar astrophysics. And in the fall of 1939, just months after Einstein's paper appeared, Oppenheimer and his graduate student Hartland Snyder published a paper that would change our understanding of gravity forever. Their question was simple. What happens when a massive star runs out of fuel? Throughout its life, a star is a battleground between two opposing forces. Gravity pulls inward, trying to crush the star into the smallest possible volume. Nuclear fusion in the core pushes outward, generating the heat and pressure that keep the star inflated. As long as fusion continues, the star is stable. But fusion cannot last forever. Eventually, the fuel runs out. And when it does, gravity wins. For most stars, the endgame is gentle. A star like our Sun will shed its outer layers and collapse into a white dwarf, a dense but stable remnant supported by a quantum mechanical effect called electron degeneracy pressure. Even though the star's nuclear fires have gone out, the electrons in its matter resist being squeezed too closely together, following the Pauli exclusion principle, a fundamental rule of quantum mechanics that forbids two identical particles from occupying the same quantum state. This pressure is enough to hold the white dwarf up against gravity, and it will remain stable essentially forever, slowly cooling and fading into darkness. A white dwarf is already an astonishing object. It packs roughly the mass of our Sun into a volume about the size of the Earth, giving it a density of about 1,000,000 grams per cubic centimeter. A teaspoon of white dwarf material would weigh about 5 tons. The gravitational field at the surface is roughly 350,000 times stronger than at the surface of the Earth. If you could somehow stand on a white dwarf, you would be crushed flat in an instant. And yet, compared to what comes next on the ladder of gravitational collapse, a white dwarf is positively fluffy. But in 1930, a 20-year-old Indian physicist named Subramanian Chandrasekhar, during a ship voyage from India to England, calculated that electron degeneracy pressure has a limit. If the mass of the collapsing core exceeds about 1.4 times the mass of the Sun, the electrons cannot support it. Gravity wins, and the core collapses further, crushing the electrons and protons together to form neutrons. The result is a neutron star, an object so dense that a teaspoon of its material would weigh about 1,000,000,000 tons. Neutron stars are supported by neutron degeneracy pressure, the same quantum exclusion principle, but now applied to neutrons. A neutron star is one of the most extreme objects in the observable universe. Its density is comparable to that of an atomic nucleus, roughly 10 to the 14 grams per cubic centimeter. It packs 1 to 2 solar masses into a sphere only about 20 kilometers across, roughly the size of a city. Its surface gravity is about 200 billion times the surface gravity of Earth. Its magnetic field can be trillions of times stronger than Earth's. A rapidly spinning neutron star emits beams of radiation from its magnetic poles, sweeping across the sky like a cosmic lighthouse. We observe these as pulsars, and their pulses are so regular that they rival atomic clocks in their precision. Chandrasekhar's discovery earned him the Nobel Prize in Physics in 1983, but at the time, his conclusion was met with fierce resistance. The great Arthur Eddington, one of the most celebrated astrophysicists of the era, publicly ridiculed Chandrasekhar's result, declaring that there should be a law of nature preventing a star from behaving in such an absurd way. Chandrasekhar was humiliated, but he was also right. What Oppenheimer and Snyder realized in 1939 was that neutron degeneracy pressure also has a limit. If the collapsing core is massive enough, roughly 2 to 3 times the mass of the Sun, depending on the equation of state, then even the neutrons cannot hold it up. No known force in physics can resist the inward pull of gravity. And so the core collapses, and it keeps collapsing, past the Schwarzschild radius, past the event horizon, down and down and down, its density climbing toward infinity, its volume shrinking toward zero, until general relativity predicts the formation of the very thing Einstein said could never exist, a singularity. Their paper, published on September 1st, 1939, stated it clearly. The star closes itself off from any communication with a distant observer. Only its gravitational field persists. A black hole, though the term would not be coined for another 3 decades, had been shown to be a plausible physical outcome of stellar death. But on that very same day, September 1st, 1939, Germany invaded Poland, and the world plunged into war. Oppenheimer's paper was largely forgotten. He himself was soon recruited to lead the Manhattan Project, the secret American effort to build an atomic bomb, and after the war, his involvement in Cold War politics and his eventual security hearing consumed whatever remained of his scientific career. He never returned to astrophysics. The man who had discovered the inevitability of gravitational collapse spent the rest of his life haunted by the consequences of nuclear physics, not gravitational physics. For nearly 2 decades after the war, singularities and gravitational collapse remained at the margins of physics. Most physicists were drawn to the exciting new world of particle physics, nuclear physics, and quantum electrodynamics, fields that seem to be producing results at a thrilling pace. General relativity was widely regarded as a beautiful but impractical theory, mathematically elegant but experimentally almost inaccessible. Departments that taught it often relegated it to a single elective course, and students who chose to specialize in it were sometimes warned that they were committing career suicide. But the universe had other plans. In the late 1950s and early 1960s, astronomers began discovering objects that could not be explained without invoking extreme gravitational phenomena. Quasars, intensely luminous point sources at cosmological distances, appeared to be releasing more energy than entire galaxies from regions smaller than the solar system. The only plausible power source was matter falling into a gravitationally collapsed object, converting its gravitational potential energy into radiation with an efficiency far exceeding nuclear fusion. X-ray sources in the Milky Way suggested compact objects of extraordinary density orbiting ordinary stars. Radio astronomers discovered pulsars, rapidly rotating neutron stars whose existence confirmed that gravitational collapse to densities beyond the white dwarf stage was not merely theoretical but real. The term black hole itself was not coined until 1967, when John Wheeler first used it at a conference in New York. Wheeler later said he adopted the phrase because it was more evocative than the existing technical terms like gravitationally totally collapsed object or frozen star, and it caught on immediately. The phrase had a certain grim poetry to it that resonated with the public imagination and transformed these abstract mathematical objects into icons of popular science. It would take another generation of physicists to build on Oppenheimer's forgotten insight and prove, beyond any reasonable mathematical doubt, that singularities are an inescapable feature of gravitational collapse. And it would be one of the most extraordinary scientific achievements of the 20th century. The singularity theorems, when Penrose and Hawking proved the inevitable. For decades after Oppenheimer and Snyder's work, a nagging question lingered. Their model was highly idealized. They had assumed perfectly spherical collapse, with no rotation, no pressure, no asymmetry of any kind. It was a mathematical exercise, elegant but potentially misleading. Perhaps in a real collapse, where matter is lumpy and rotating and subject to all sorts of complicated forces, the singularity would not form. Perhaps the matter would bounce, or swirl, or fragment, or somehow avoid that fatal point of infinite density. The singularity might be nothing more than a consequence of unrealistic simplicity. This was not an unreasonable hope. In the early 1960s, the Soviet physicists Yevgeny Lifshitz and Isaac Kalatnikov published calculations suggesting that singularities did not form in the general case. Their analysis indicated that the tiniest deviations from perfect symmetry would be enough to prevent the collapse from reaching a singularity. If correct, this would have been a profound relief. The universe would be free of these pathological points. Einstein would have been vindicated, but they were wrong, and the person who proved it was a quiet, brilliant mathematician named Roger Penrose. Penrose was born in 1931 in Colchester, England, the son of a geneticist and the brother of a chess grandmaster. He showed mathematical talent from an early age and went on to study at University College London and Cambridge before taking a position at Birkbeck College in London. By the early 1960s, he had become deeply interested in the mathematical structure of spacetime and had begun developing powerful new tools for analyzing it. In 1965, Penrose published a short paper in Physical Review Letters that would earn him the Nobel Prize in Physics 55 years later. It was just 2 pages long, but it contained one of the most important results in the history of general relativity. What made Penrose's approach so revolutionary was that he abandoned the traditional method of solving Einstein's equations explicitly. Previous work on singularities had always involved finding specific solutions, like Schwarzschild's or Oppenheimer and Snyder's, and then checking whether those particular solutions contained singularities. This approach was limited because it could only tell you about the specific cases you happened to solve, and the critics could always argue that a slightly different, more realistic scenario might avoid the singularity. Penrose did something far more powerful. He proved a theorem that applied not to any specific solution, but to all solutions satisfying certain general conditions. He used the global topological and causal structure of spacetime, rather than its specific local geometry, to demonstrate that singularities were inescapable. Penrose introduced a revolutionary concept, the trapped surface. Imagine a sphere of light emitted from a region of spacetime. In normal conditions, the outward-pointing light rays diverge. They spread apart, expanding the sphere. But in a region of sufficiently intense gravity, something remarkable happens. Even the outward-pointing light rays converge. They are forced inward by the curvature of spacetime. The sphere of light shrinks, no matter which direction it tries to expand. Once a trapped surface forms, Penrose showed, the collapse cannot be reversed. Think of it this way. In everyday experience, if you shine a flashlight outward from a spot, the light spreads out. The sphere of illumination grows. But deep inside a region of extreme gravitational collapse, even the outward-facing light is being dragged inward. There is no direction you can point a flashlight where the light escapes. The trap is complete, and Penrose proved that once this trap snaps shut, something terrible follows. Under very general conditions, requiring only that gravity is attractive, technically, that the energy density of matter is non-negative, and that the spacetime has a reasonable large-scale structure, the existence of a trapped surface guarantees that the spacetime contains incomplete geodesics, paths through spacetime that simply end after a finite amount of time. This is what physicists mean by a singularity in the context of the Penrose theorem. It does not say that the density becomes infinite, or that the curvature blows up, though those things are widely expected to happen. What it says is that there are paths through spacetime, the paths that freely falling particles and light rays follow, that cannot be extended indefinitely. They run into something. They hit a wall. The story of their existence comes to an abrupt and unexplainable end. Penrose's theorem was devastating in its generality. It did not depend on perfect spherical symmetry. It did not require any special assumptions about the matter involved. It applied to realistic, lumpy, spinning, complicated collapses. As long as a trapped surface formed, a singularity was inevitable. The Lifshitz-Kalat-Naikov claim that small deviations from symmetry could prevent singularity formation was overturned. Lifshitz and Kalat-Naikov later acknowledged the error in their analysis and corrected it, and in fact Kalat-Naikov himself became one of the contributors to the theory of singularities in more general spacetimes. The impact of Penrose's theorem rippled through the physics community like a shockwave. For years, physicists had clung to the hope that singularities were artifacts of oversimplification, that real-world messiness would somehow save the universe from these pathological points. Penrose had closed that escape route. His theorem was not about specific solutions, but about the topological structure of spacetime itself. It used concepts from differential geometry, particularly the behavior of geodesic congruences, families of paths through spacetime that converge or diverge under the influence of gravity, to show that certain spacetimes are geodesically incomplete. The mathematics was rigorous, the assumptions were minimal, and the conclusion was iron. The two-page paper would earn Penrose a share of the 2020 Nobel Prize in Physics, more than half a century after its publication. The Nobel Committee cited his discovery that black hole formation is a robust prediction of the general theory of relativity. It was one of the longest waits between a discovery and its Nobel recognition in the history of the prize. But Penrose's theorem was just the beginning. A young physicist at Cambridge named Stephen Hawking realized that the same geometric techniques could be applied not just to collapsing stars, but to the entire universe. Hawking had been diagnosed with amyotrophic lateral sclerosis, ALS, in 1963 at the age of 21. He was given 2 years to live. The diagnosis initially plunged him into depression, but an unexpected reprieve. The disease progressed far more slowly than expected, combined with his engagement to Jane Wilde, reignited his passion for physics. Against all expectations, he survived for more than half a century, eventually losing the ability to walk, to write, to speak without the aid of a computer, and yet producing some of the most consequential ideas in the history of physics. His wheelchair and his synthesized voice became iconic symbols of the triumph of the human mind over physical limitation. One of his first major contributions, in the late 1960s, was to extend Penrose's singularity theorem to cosmology. The key insight was elegant in its simplicity. Penrose had shown that if you had a trapped surface, a region where gravity was pulling everything inward so strongly that even outward-pointing light converged, then a singularity was inevitable in the future. Hawking realized that you could flip this argument around. The universe is expanding. Run the clock backward, and it is contracting. If the contraction is severe enough, then in the time-reversed picture, there must be a trapped surface. And if there is a trapped surface in the time-reversed picture, then there is a singularity, but now in the past. The Big Bang singularity. If you take the observed expansion of the universe and run the clock backward, the universe gets denser and hotter. Galaxies come closer together. The cosmic microwave background gets more intense. The conditions get more extreme. And if you keep going, following the equations of general relativity all the way back, you arrive at a state of infinite density and temperature at a finite time in the past. The Big Bang singularity. Hawking showed that, under reasonable assumptions about the matter content of the universe, this singularity was unavoidable. The universe must have begun in a singular state. Not just in the idealized Friedman models that cosmologists used as simple approximations, but in the real, complicated, lumpy universe we actually observe. In 1970, Penrose and Hawking published a joint paper that unified their results into a single, powerful theorem. The Penrose-Hawking singularity theorem established that singularities are a generic feature of general relativity. They are not artifacts of special symmetry. They are not products of unrealistic assumptions. They are consequences of gravity being attractive, of matter having positive energy, and of spacetime having a reasonable causal structure. The theorem was a watershed moment. It meant that general relativity, our best theory of gravity, predicts its own breakdown. The theory is self-aware enough to tell us that there are situations where it cannot make predictions, where its equations produce meaningless infinities, where the smooth fabric of spacetime itself comes to an end. And rather than being exotic or unlikely, these situations are common. Every black hole contains one. The universe began with one. It was a profound and humbling result. And it launched an entirely new era in theoretical physics, one devoted to understanding the nature of these singular points and finding a deeper theory that might resolve them. The Big Bang singularity, where time itself begins. Of all the singularities that general relativity predicts, none is more consequential than the one at the beginning of the universe. The story of the Big Bang is, in many ways, the story of modern cosmology. In the 1920s, the Belgian priest and physicist Georges Lemaitre, working with Einstein's field equations, realized that the universe need not be static. It could be expanding. He proposed that the cosmos began as what he poetically called a primeval atom, a state of incredible compression from which everything we see today emerged. Around the same time, the Russian mathematician Alexander Friedmann had independently found similar expanding solutions to Einstein's equations. The observational confirmation came in 1929 when Edwin Hubble measured the redshifts of distant galaxies and found that they were all moving away from us, with more distant galaxies receding faster. The universe was expanding, and if it was expanding now, then in the past it must have been smaller, denser, and hotter. Run the movie backward far enough, and you arrive at a state of extraordinary compression. But how far back can you go? General relativity, combined with the observed expansion rate and the matter content of the universe, gives a clear answer. You can trace the expansion backward approximately 13.8 billion years, and as you do, the density and temperature of the universe climb without limit. The scale factor, the mathematical quantity that describes the size of the universe, shrinks to zero. The density diverges to infinity. The temperature diverges to infinity. The curvature of spacetime diverges to infinity. You have arrived at the initial singularity. At the Big Bang singularity, the equations of general relativity break down completely. Space and time, as described by the theory, cease to be well defined. You cannot ask what happened before the Big Bang, because before is a temporal concept, and time itself begins at the singularity. It is not that the universe was empty before the Big Bang, and then suddenly filled with matter and energy. It is that there was no before. The singularity is the boundary of space-time, the edge of existence, the point beyond which the theory offers only silence. This concept is among the hardest in all of physics to grasp, not because it is mathematically complicated, but because it defies our most basic intuitions about time and causation. We are creatures of time. Our entire experience of reality is structured by the flow of past into present into future. The idea that time itself had a beginning, that there is a limit in the past beyond which the question, what happened before, is literally meaningless, is alien to the way our minds naturally work. The physicist Stephen Hawking often used an analogy with the surface of the Earth to make the point more accessible. Asking what happened before the Big Bang, he said, is like asking what lies south of the South Pole. The question is grammatically correct, but physically meaningless. The South Pole is the southernmost point on Earth. There is no farther south to go. Similarly, the Big Bang singularity, or whatever replaces it in a quantum theory of gravity, is the earliest moment of time. There is no earlier moment to ask about. The Planck epoch, the period before about 10 to the minus 43 seconds after the Big Bang, is the great frontier. During this unimaginably brief interval, the temperature of the universe would have exceeded the Planck temperature of about 1.4 times 10 to the 32 Kelvin, and the density would have exceeded the Planck density of about 5 times 10 to the 93 grams per cubic centimeter. At these conditions, the gravitational interactions between quantum particles become as strong as the other fundamental forces. General relativity alone cannot describe what happens. Quantum mechanics alone cannot describe what happens. Only a theory that unifies them, a theory of quantum gravity, could penetrate this veil. The Planck epoch is named after Max Planck, the German physicist who, in 1899, 3 years before Einstein's first paper on relativity and a quarter century before quantum mechanics was fully developed, realized that the fundamental constants of nature, the speed of light, Newton's gravitational constant, and the quantum of action that now bears his name, could be combined to define natural units of length, time, mass, and temperature. These Planck units, as they came to be called, represent the scales at which quantum gravitational effects become dominant. The The Planck length is about 1.6 times 10 to the minus 35 meters, about 10 trillion times smaller than a proton. The Planck time is about 5.4 times 10 to the minus 44 seconds. The Planck mass is about 22 micrograms, roughly the mass of a small grain of sand, which may seem modest until you realize it is the mass squeezed into a volume defined by the Planck length, giving the Planck density its staggering value. At the Planck scale, the smooth, continuous spacetime described by general relativity is expected to break down. Quantum fluctuations in the geometry of spacetime become violent and uncontrollable. Space is no longer a smooth fabric, but a seething quantum foam, bubbling and churning at scales too small to observe with any conceivable experiment. The very concept of distance may lose its meaning. The very concept of time may become fuzzy, uncertain, subject to quantum fluctuations that make it impossible to define a precise before and after. This is a deeply unsatisfying state of affairs for scientists who want to understand the origin of everything. And there are good reasons to suspect that the Big Bang singularity, while predicted by classical general relativity, may not be a physically real feature of the universe. The first reason is that general relativity is a classical theory. It does not incorporate quantum mechanics. And we know from the rest of physics that quantum effects become important at extremely small scales and high energies. The conditions near the Big Bang singularity would have been so extreme that quantum gravitational effects, whatever they might be, would certainly have been dominant. The density would have exceeded the Planck density, roughly 10 to the 93 grams per cubic centimeter, a number so absurdly large that it defies comprehension. The temperature would have been near the Planck temperature, about 10 to the 32 Kelvin. At these scales, the smooth spacetime described by general relativity is expected to dissolve into something fundamentally different, perhaps a seething quantum foam of fluctuating geometry, perhaps something even more exotic. We simply do not know. The second reason is observational. The tremendous success of inflationary cosmology, the idea that the very early universe underwent a period of exponentially rapid expansion, suggests that whatever initial state preceded inflation may not have been a singularity at all. Inflation, proposed by Alan Guth in 1981, solves several deep puzzles about the universe, including why it appears so spatially flat, why it is so uniform in temperature across vast distances, and why we do not observe certain exotic relics like magnetic monopoles that many grand unified theories predict should have been produced in the early universe. But inflation also changes the picture of the very beginning. In an inflationary universe, the conditions before inflation began may have been very different from the singular state predicted by classical general relativity. There is, to this day, no direct observational evidence of the Big Bang singularity itself. The earliest moment we can observe directly is the era of recombination, roughly 380,000 years after the Big Bang, when the universe cooled enough for electrons to combine with nuclei to form neutral atoms, allowing light to travel freely for the first time. This light, the cosmic microwave background radiation, is the oldest signal we can detect. It tells us about the conditions of the young universe, and it is consistent with the hot Big Bang model. But it cannot tell us what happened at the very beginning, during the Planck epoch, the first 10 to the minus 43 seconds, when quantum gravity would have ruled and our current theories are mute. The Big Bang singularity therefore occupies a strange position in our understanding. It is predicted by general relativity, confirmed, in a sense, by the Penrose-Hawking singularity theorems, and consistent with the observed expansion and cooling of the universe. But it is also widely suspected to be an artifact of applying a classical theory beyond its domain of validity. Most physicists believe that a true theory of quantum gravity will replace the singularity with something else, something finite, something comprehensible, something that avoids the embarrassment of infinite density and zero volume. But what that something is remains one of the great open questions in all of science. Some approaches, like loop quantum cosmology, suggest that the Big Bang was actually a big bounce, a transition from a previous contracting phase of the universe to the expanding phase we observe today. In this picture, the density never reaches infinity. Instead, it reaches a maximum, finite value at the Planck scale, and then the universe rebounds. The singularity is replaced by a smooth, if extreme, moment of transition. Other approaches, like string cosmology and the Hartle-Hawking no-boundary proposal, offer their own alternatives, each with different implications for the nature of time and the origin of the cosmos. The Hartle-Hawking proposal, first articulated by Hawking and James Hartle in 1983, deserves a moment of attention for its sheer audacity. Hawking and Hartle suggested that the universe has no boundary in time. Rather than imagining the Big Bang as a moment where time begins at a sharp edge, they proposed that as you approach the very beginning, time gradually becomes indistinguishable from space. The singularity is not eliminated by some physical mechanism that prevents infinite compression. Instead, it is eliminated by the geometry of space-time itself becoming smooth and rounded, like the South Pole of the Earth. You can walk to the South Pole, and there is nothing special about being there. You do not fall off the edge of the world. Similarly, in the Hartle-Hawking proposal, you can approach the beginning of the universe, and there is nothing pathological about it. Time simply fades into space, and the question, what came before the Big Bang, becomes as meaningless as asking, what is south of the South Pole? Hawking described this idea in A Brief History of Time, and it became one of the most famous metaphors in all of popular science. But all of these remain speculative. None has been confirmed by observation. The Big Bang singularity, whether real or not, continues to mark the limit of our knowledge. It is the wall beyond which we cannot yet see, the horizon beyond which science has not yet learned to peer. It is worth pausing here to appreciate what the combination of observation and theory has given us. We can trace the history of the universe with remarkable confidence back to about 1 second after the Big Bang, when the universe was a dense plasma of protons, neutrons, electrons, and neutrinos at a temperature of roughly 10 billion degrees. The predictions of Big Bang nucleosynthesis, which describe how the lightest elements, hydrogen, helium, and traces of lithium, were forged in the first few minutes, match the observed abundances with impressive accuracy. We can see the afterglow of the universe's transition from opaque plasma to transparent gas in the cosmic microwave background, and its detailed patterns of temperature fluctuations match the predictions of inflationary cosmology with exquisite precision. We can even detect the subtle imprint of primordial gravitational waves in the polarization of that ancient light, though the details of that detection remain a subject of active research. But we cannot trace the universe's history all the way back to the moment of its birth. The laws of physics as we know them cease to be trustworthy below the Planck time, roughly 10 to the minus 43 seconds after the supposed singularity. Before that moment, quantum gravitational effects dominate, and we have no reliable theory to guide us. The singularity sits behind this curtain of ignorance, beckoning us forward but refusing to reveal itself. And if the singularity at the beginning of the universe is mysterious, the singularities inside black holes are even more so. Because those singularities are not merely theoretical. They are, if general relativity is correct, forming right now, hidden behind event horizons, sealed off from the outside universe, as massive stars collapse and die across the cosmos. What would it be like to fall toward one of them? Into the abyss, what it would be like to fall toward a singularity. Imagine, for a moment, that you have decided to do something extraordinarily foolish. You have piloted your spacecraft to the vicinity of a stellar mass black hole, a dark remnant about 10 times the mass of our Sun, lurking in the void between the stars. Its event horizon is roughly 30 kilometers across, about the size of a small city. From a safe distance, you can see it only by the way it bends the light from stars behind it, creating a dark shadow rimmed by a distorted halo of warped starlight. It is eerily beautiful, and you have decided to fly into it. As you begin your approach, everything seems normal at first. The gravitational pull is noticeable but manageable, no different in principle from orbiting any massive object. If you maintained a safe distance, you could orbit the black hole for as long as you liked. But you are not maintaining a safe distance. You are falling inward. The first thing you notice, before anything dramatic happens, is the tidal force. Gravity is not uniform. It is stronger closer to the source and weaker farther away. This means that if you are falling feet first toward the black hole, the gravitational pull on your feet is slightly stronger than the pull on your head. This difference tries to stretch you along the direction of fall and compress you from the sides. Near our Sun, this tidal difference across the length of a human body is vanishingly small. Near a stellar mass black hole, it becomes extreme. Physicists have a wonderfully evocative name for what happens next: spaghettification. As you fall closer to the black hole, the tidal forces intensify. Your body is stretched vertically and squeezed horizontally. Your feet accelerate faster than your head. The difference in gravitational pull across even the length of your body becomes enormous. At some point, the stretching force exceeds the strength of the molecular bonds holding your body together. You are pulled apart, first at the weakest point, probably somewhere around the midsection. Then the two halves are themselves stretched and pulled apart, and then those pieces, and so on, in an accelerating cascade of disintegration, until you are nothing but a thin stream of individual atoms, a river of subatomic debris spiraling inward toward the singularity. Stephen Hawking was one of the first physicists to describe this process in popular terms. In his landmark book, A Brief History of Time, he imagined an unfortunate astronaut falling into a black hole and being stretched like spaghetti. The image stuck, and spaghettification became part of the lexicon of popular science. The word itself was coined by Hawking, and it has a light-hearted quality that belies the absolute horror of the process it describes. But there is an important subtlety here, one that reveals something deep and counterintuitive about the nature of gravity itself. The point at which spaghettification becomes lethal depends on the mass of the black hole, and the relationship is perhaps the opposite of what you might expect. For a small stellar mass black hole, the tidal forces at the event horizon are absolutely ferocious. You would be torn apart long before you reach the horizon. For a supermassive black hole, like the ones that sit at the centers of galaxies and can be millions or billions of times the mass of the Sun, the tidal forces at the event horizon are surprisingly gentle. The event horizon of a supermassive black hole is so far from the singularity at its center that the gravitational gradient across a human body is practically negligible. You could cross the event horizon of the black hole at the center of the Milky Way, Sagittarius A star, which is about 4 million solar masses, without feeling a thing. But make no mistake, you are still doomed. Once inside the event horizon, every possible trajectory leads inward. There is no path outward, no matter how powerful your engines, because the curvature of spacetime inside the event horizon is so extreme that all directions in space point toward the singularity. It is not that the gravitational pull is too strong to escape. It is that the very geometry of space has been warped so that outward does not exist anymore. Moving toward the singularity is not like moving through space. It is more like moving through time. Just as you cannot avoid tomorrow, you cannot avoid the singularity once you have crossed the event horizon. It lies in your future, as inescapable as the passage of seconds. And so you fall inside the event horizon of a supermassive black hole. You might have hours or even days of subjective time before the tidal forces become unbearable. During that time, your view of the outside universe would be bizarre and distorted, a shrinking circle of light above you as space-time warps the paths of photons entering the black hole. The light of stars would be blue shifted to higher and higher energies as the photons fall alongside you in the increasingly warped geometry. You would also notice something deeply counterintuitive about the nature of space inside the event horizon. In the normal universe, space is something you can move through in any direction. You can go left, right, forward, backward, up, or down. Time, by contrast, flows in one direction, forward. But inside a non-rotating black hole, something astonishing happens. The roles of space and time become interchanged in the radial direction. The inward direction toward the singularity is no longer a direction in space. It has become a direction in time. You cannot avoid the singularity for the same reason you cannot avoid tomorrow. Moving outward would be like trying to move backward in time, something the laws of physics strictly forbid. This means that inside the event horizon, the singularity is not a place. It is a moment in your future that you will inevitably reach, no matter what you do. You could fire your engines at full power. You could turn around and try to fly outward. It would not help. Every possible trajectory, every conceivable path through the distorted space-time inside the event horizon leads to the singularity. It is not ahead of you in space. It is ahead of you in time, and time moves only forward. The psychological horror of this situation is difficult to overstate. Imagine knowing, with mathematical certainty, that your existence will end at a specific future moment, and that nothing you do can change it. Imagine knowing that the laws of physics themselves have conspired to make your destruction inevitable. That is what it would be like inside a black hole. Eventually, no matter the mass of the black hole, the tidal forces catch up with you. They grow and grow and grow, and there is nothing to stop them. As you approach the singularity, the stretching and compression become infinite. Every atom, every quark, every fundamental particle that makes up your body is pulled apart and crushed together simultaneously. This is the spaghettification taken to its ultimate conclusion. At the singularity itself, according to general relativity, the curvature of space-time is infinite, the density is infinite, and the tidal forces are infinite. What happens to the matter that arrives there is simply not described by the theory. The equations break down. The story ends. But it is worth lingering on this moment a little longer, because the breakdown at the singularity is not just a failure of prediction. It is a failure of description. General relativity cannot tell you what the singularity is made of. It cannot tell you what happens to the matter and energy that reach it. It cannot tell you whether the matter is destroyed, transformed, transmitted elsewhere, or frozen in some eternal state. The theory literally does not have the vocabulary to discuss what occurs at this point. It is as if you were reading a book, following a compelling narrative, and then mid-sentence the words dissolved into meaningless symbols. Not a bad ending. Not an unsatisfying ending. No ending at all. Just an abrupt and complete cessation of sense. Or does it? Perhaps, if the black hole is spinning, the story is more complicated than that. Much more complicated. The spinning darkness, Kerr black holes, and the ring singularity. For nearly half a century after Schwarzschild found his solution, the only black holes that general relativity could precisely describe were the most unrealistic ones. Perfectly spherical, perfectly still, floating in an otherwise empty universe. Real black holes, The ones formed by the deaths of massive stars are nothing like this. Real stars spin, and when they collapse, they carry their angular momentum with them, meaning the resulting black hole spins too. In fact, most of the black holes in the universe are expected to be spinning, many of them quite rapidly. The challenge of finding an exact solution to Einstein's equations for a rotating black hole turned out to be one of the hardest problems in general relativity. It resisted the efforts of mathematicians and physicists for decades. Many tried. Some came close. But the nonlinearity of Einstein's field equations, the way every part of the solution depends on every other part, made the rotating case ferociously difficult compared to the static, spherical case that Schwarzschild had solved. Then, in 1963, a New Zealand mathematician named Roy Kerr cracked it. Kerr was 30 years old at the time, working at the University of Texas at Austin. He had been born in the small town of Kuro on New Zealand's South Island and had earned his doctorate from Cambridge before moving to the United States. He had been studying the problem of axially symmetric solutions to Einstein's equations, a fiendishly difficult mathematical challenge that required a blend of physical intuition and algebraic virtuosity. Using a sophisticated set of techniques involving what are now called Kerr-Schild metrics, he found an exact solution describing the spacetime around a rotating, uncharged mass. The story of its announcement is remarkable. When Kerr presented his solution at the first Texas Symposium on Relativistic Astrophysics in December 1963, the audience was largely unimpressed. The conference was buzzing about the recent discovery of quasars, immensely luminous objects at cosmological distances, and most attendees were more interested in astrophysical observations than abstract mathematical solutions. The legendary astrophysicist Subramanian Chandrasekhar later recalled that when Kerr finished his brief talk, the audience barely reacted. It would take years for the physics community to fully appreciate the magnitude of what he had found. The Kerr metric, as it came to be known, was the first realistic black hole solution, the one that actually described the kind of black holes that nature creates. Nobel laureate S. Chandrasekhar would later call it the most shattering experience of his scientific career when he finally understood the full implications of Kerr's solution. And the interior of a Kerr black hole was far stranger than anyone had anticipated. Unlike the Schwarzschild black hole, which has a single event horizon surrounding a point singularity, the Kerr black hole has two event horizons, an outer one and an inner one, sometimes called the Cauchy horizon. Between them is a region of bizarre physics where frame dragging, the tendency of a spinning mass to twist spacetime around it, becomes overwhelming. Any object in this region is forced to rotate along with the black hole, carried helplessly by the current of twisted spacetime. But there is an even stranger region outside the outer event horizon, the ergosphere. The ergosphere is an oblate zone, bulging at the equator, where frame dragging is so powerful that nothing, not even light, can remain stationary relative to distant observers. You are dragged along in the direction of the black hole's rotation whether you want to be or not. Yet unlike being inside the event horizon, you can still escape from the ergosphere. You are forced to rotate, but you are not forced to fall in. This creates one of the most remarkable theoretical possibilities in all of physics. In 1969, Roger Penrose showed that the ergosphere allows for a process, now called the Penrose process, in which energy can actually be extracted from a spinning black hole. An object entering the ergosphere can split into two pieces, one falling into the event horizon and the other escaping with more energy than the original object brought in. The extra energy comes from the black hole's rotational energy. In principle, you could mine a rotating black hole for energy, slowing its spin in the process. The efficiency of this extraction can reach nearly 30% of the rest mass energy of the infalling material, far exceeding even nuclear fusion. If advanced civilizations exist elsewhere in the cosmos, some theorists have speculated the Penrose process might be the ultimate power source. But the most dramatic difference is at the center. In a Schwarzschild black hole, the singularity is a single, dimensionless point. In a Kerr black hole, the singularity is a ring of zero thickness but finite radius, lying in the equatorial plane of the black hole's rotation. This ring singularity, sometimes called a ringularity, is a consequence of the angular momentum of the collapsing matter. A point cannot support rotation in classical physics, so the minimum shape that can carry angular momentum is a ring. The ring singularity of a Kerr black hole has properties that border on science fiction. Unlike the point singularity of a Schwarzschild black hole, which lies in the future of every object that crosses the event horizon and is therefore unavoidable, the ring singularity of a Kerr black hole is time-like. It exists at a particular location in space rather than at a particular moment in time. And this means, at least in the idealized mathematical description, that it might be avoidable. An object falling into a Kerr black hole might be able to thread itself through the center of the ring without ever hitting the singularity. What would it find on the other side? According to the maximally extended Kerr solution, the mathematical structure of the spacetime, if you push it to its logical limits, passing through the ring singularity would take you into an entirely new region of spacetime, a region with negative mass, a region where gravity is repulsive, a region that some theorists describe as an anti-universe, a mirror image cosmos with inverted physical laws. Even more astonishing, the mathematical extension of the Kerr geometry contains closed time-like curves, paths through spacetime that loop back on themselves, creating the theoretical possibility of time travel. Near the ring singularity, the frame-dragging effect of the spinning black hole becomes so extreme that it warps not just space, but time into closed loops. It is a dizzying picture. But physicists are quick to caution that these exotic features of the Kerr solution may not survive contact with reality. The Kerr metric describes an idealized, eternal black hole. A real black hole, formed from collapsing matter, would have a different internal structure. The inner event horizon of the Kerr solution is known to be unstable. Any radiation or matter falling inward is infinitely blue-shifted at this surface, meaning its energy is amplified without limit. This blue shift instability is expected to transform the inner horizon into a singularity of its own, a chaotic boundary that would destroy any object trying to pass through. And the ring singularity itself? Roy Kerr himself, in a provocative paper published in 2023 at the age of 89, argued that the ring singularity might not physically exist at all. He pointed out that the Penrose singularity theorem proves that certain geodesics, paths through spacetime, are incomplete, but it does not necessarily prove that those paths terminate at a region of infinite curvature. Kerr suggested that the interior of a real rotating black hole might contain not a singularity, but a dense, non-singular object, perhaps something like a stabilized remnant of the collapsed star's core. If he is correct, then one of the most iconic features of black hole physics, the singularity at the center, might be nothing more than a mathematical phantom. The debate continues, and it connects directly to one of the biggest questions in gravitational physics: whether nature allows singularities to be seen from the outside, or whether it always hides them behind event horizons. Naked singularities and the cosmic sensor. If a singularity is a place where physics breaks down, then a natural question arises. What would happen if a singularity were exposed to the outside universe? What if there were no event horizon shielding it from view? What would we see? And more importantly, what would it do? This is the question of naked singularities, and it has troubled physicists since the earliest days of black hole research. A naked singularity would be, in a sense, an open wound in space-time, a place where the laws of physics fail and yet whose effects can reach the rest of the universe. It could, in principle, emit anything: particles, radiation, information, influences that are completely unpredictable because they originate from a region where no physical law applies. The prospect was disturbing enough that in 1969, Roger Penrose proposed what he called the cosmic censorship hypothesis. It came in two flavors. The weak cosmic censorship hypothesis states that any singularity formed by gravitational collapse in a physically realistic situation will always be hidden behind an event horizon. The universe, in Penrose's evocative phrase, has a cosmic censor that forbids naked singularities, clothing them in event horizons before they can offend the sensibilities of distant observers. The strong cosmic censorship hypothesis goes further. It states that the region of space-time that can be predicted from initial conditions, the maximal Cauchy development, in technical language, is inextendable. In simpler terms, determinism holds. Given the state of the universe at one moment, the laws of physics can predict its future. Naked singularities would destroy this predictability because influences from the singularity could not be accounted for in any advanced calculation. Strong cosmic censorship says the universe does not permit this. The cosmic censorship hypothesis is not a proven theorem. It is a conjecture, one of the most important open problems in general relativity. Despite more than 50 years of effort by some of the brightest minds in theoretical physics, it has neither been proven nor definitively disproven. There have been tantalizing hints in both directions. In 1991, physicists Stuart Shapiro and Saul Tucholsky ran computer simulations of the collapse of a rotating spindle of dust and found conditions under which a naked singularity appeared to form. The result was sensational. It suggested that cosmic censorship could be violated. This led to one of the more colorful episodes in the history of physics. In 1991, John Preskill and Kip Thorne bet against Stephen Hawking that cosmic censorship was false. When the Shapiro-Tucholsky results came in, Hawking conceded the bet, but with a caveat: the simulations relied on special circumstances, perfectly spindle-shaped dust with no pressure, and he argued these were technicalities that a more refined statement of the hypothesis would exclude. The bet was reformulated, this time with a requirement that the violation occur under generic conditions. The prize for the winner? Clothing to cover the winner's nakedness. The revised bet remained unresolved at the time of Hawking's death in 2018. More recent work has deepened the mystery. In 2017, Toby Crisford and Jorge Santos found numerical evidence for the violation of weak cosmic censorship in four-dimensional anti-de Sitter spacetime, a mathematical idealization of the universe with a negative cosmological constant. This was a significant result, but anti-de Sitter space is not our universe. Whether the violation extends to the asymptotically flat spacetime of the real cosmos remains unknown. On the other hand, there are strong arguments in favor of cosmic censorship. In the spherically symmetric case, Dimitrios Christodoulou proved that for a collapsing scalar field, naked singularities can form, but only for a set of initial conditions of measure zero, meaning they are infinitely unlikely to occur in practice. The generic collapse leads to a black hole with a singularity safely hidden behind an event horizon. There is also a fascinating connection to the weak gravity conjecture, an idea from string theory suggesting that in any consistent theory of quantum gravity, the gravitational force must be the weakest force. Qumran Vafa of Harvard has argued that the weak gravity conjecture, if true, would automatically save cosmic censorship by preventing the conditions needed to form naked singularities from ever being physically realized. The question of naked singularities matters for more than just mathematical elegance. If cosmic censorship holds, then the universe, despite containing singularities inside every black hole, remains deterministic outside those black holes. The event horizons are perfect membranes that contain the damage. The singularities are sealed off, unable to affect the broader cosmos. Physics continues to make sense for everyone who stays outside. But if cosmic censorship fails, then we live in a universe where pockets of space-time can spontaneously generate unpredictable influences, where the past does not determine the future, where the laws of physics have holes that cannot be patched. It would be, as Penrose himself suggested, a disaster for physics. To understand why this is such a disaster, consider what a naked singularity would actually look like from the outside. A black hole singularity is invisible. It is hidden behind an event horizon, and whatever chaos it produces is confined to the interior. A naked singularity, by contrast, is visible. Photons can escape from arbitrarily close to it. Particles can be ejected from its vicinity. And because the curvature of space-time diverges at the singularity, these photons and particles can carry arbitrarily high energies. They can have been affected by physics we do not understand, physics at the Planck scale or beyond, and they can bring those effects into the outside universe. A naked singularity is not just a theoretical embarrassment. It is an uncontrolled source of unpredictable physics leaking into the cosmos. There is another way to think about the danger. In Newtonian physics and in general relativity with cosmic censorship, the universe is what physicists call globally hyperbolic. This means that if you know the state of the universe on one complete spatial surface, one snapshot of everything everywhere at a single moment, then the laws of physics determine the entire future. The universe is, in principle, fully predictable. A naked singularity destroys this property. Because influences from the singularity can propagate outward, and those influences are not determined by any prior state of the universe, the future becomes indeterminate. You can know everything about the present and still not predict what happens next. For a physicist, this is close to the worst possible outcome. It means the universe contains regions that are, in the most fundamental sense, unknowable. Some physicists have taken a different view, arguing that naked singularities, if they exist, might actually be useful. They would provide a window into the Planck scale physics that event horizons normally hide from us. If quantum gravity effects become visible near a naked singularity, then observations of such objects could provide direct empirical evidence for the theory of quantum gravity, something that is otherwise extraordinarily difficult to obtain. In this view, naked singularities are not disasters, but opportunities, cosmic laboratories where the deepest laws of physics are on display. Most physicists suspect that nature is a good censor. The accumulating evidence, both from mathematical proofs in simplified settings and from numerical simulations in more realistic ones, suggests that cosmic censorship holds in the generic case. The naked singularities that have been found tend to be fragile, requiring precisely tuned initial conditions that are unlikely to occur in nature. But until the conjecture is proven in full generality, a shadow of doubt remains. And that doubt, like the singularity itself, points toward a deeper theory that we have not yet found. The information paradox. What singularities do to knowledge? Singularities do not just threaten the geometry of space-time. They threaten something even more fundamental: information. In 1974, Stephen Hawking dropped a bombshell on the world of physics. Building on earlier work by Jacob Bekenstein, who had shown that black holes possess entropy proportional to the area of their event horizons, Hawking applied the principles of quantum field theory to the curved spacetime near a black hole's event horizon and made a stunning discovery. Black holes are not perfectly black. They emit radiation. Bekenstein's contribution deserves attention in its own right. As a graduate student at Princeton in the early 1970s, working under the supervision of John Wheeler, Bekenstein had been troubled by a thought experiment. Suppose you take a hot cup of coffee and throw it into a black hole. The coffee has entropy, a measure of its thermodynamic disorder. Once it crosses the event horizon, that entropy disappears from the observable universe. But the second law of thermodynamics states that the total entropy of a closed system can never decrease. Has the second law been violated? Bekenstein proposed a radical solution. He argued that the black hole itself has entropy, and that this entropy is proportional to the area of its event horizon, not its volume. When the coffee crosses the horizon grows, and the black hole's entropy increases by at least as much as the entropy of the coffee. The second law is saved. But the idea that a black hole, which appears to be the simplest possible object in physics, characterized entirely by just its mass, charge, and spin, could have enormous entropy was deeply counterintuitive. Entropy counts the number of microscopic arrangements that correspond to a given macroscopic state. A high entropy means many possible microstates. What are the microstates of a black hole? What internal structure could give rise to this entropy? The singularity at the center, where all the matter has been compressed to a single point, seems to leave no room for internal complexity. This puzzle, the microscopic origin of black hole entropy, remains one of the deepest unsolved problems in physics. String theory has had some notable successes in accounting for the entropy of certain special classes of black holes, but a general answer remains out of reach. Hawking initially disagreed with Bekenstein's idea. If a black hole has entropy, it must have a temperature. And if it has a temperature, it must radiate. But nothing escapes from a black hole. So how could it radiate? The resolution came when Hawking performed a careful calculation of quantum field theory in the curved spacetime near the event horizon. This radiation, now known as Hawking radiation, arises from the quantum mechanical behavior of fields in the extreme gravitational environment near the event horizon. The details involve the vacuum state of quantum fields becoming observer-dependent in curved spacetime, a subtle and deeply technical effect that draws on some of the most sophisticated mathematics in theoretical physics. The essence of the mechanism is that the intense gravitational field near the event horizon can convert virtual particle-antiparticle pairs, which constantly fluctuate in and out of existence in the quantum vacuum, into real particles. One particle of the pair falls into the black hole, while the other escapes to infinity. The escaping particle carries positive energy, and by the conservation of energy, the infalling particle effectively carries negative energy, reducing the mass of the black hole by a tiny amount. But the bottom line was clear and shocking. Black holes radiate. They have a temperature, and because they radiate energy, they lose mass. Over incredibly long timescales, a black hole will shrink, its temperature rising as its mass decreases, until it eventually evaporates entirely. The timescales involved are almost incomprehensibly long. A stellar mass black hole, perhaps 10 times the mass of our Sun, has a Hawking temperature of roughly 6 billionths of a Kelvin, far below the current temperature of the cosmic microwave background at about 2.7 Kelvin. This means that in the present-day universe, such a black hole actually absorbs more energy from the ambient radiation of the cosmos than it emits via Hawking radiation. It is growing, not shrinking. Only in the far future, after the universe has expanded and cooled enough for its background temperature to drop below the black hole's Hawking temperature, will evaporation begin in earnest. And once it does, the process is glacially slow. The estimated evaporation time for a stellar mass black hole is roughly 10 to the 67 years. For the supermassive black holes at the centers of galaxies, the evaporation time stretches to 10 to the 100 years or beyond, timescales so vast that they make the current age of the universe, about 13.8 billion years, seem like the blink of an eye. This was remarkable enough on its own. But Hawking went further. He showed that the radiation emitted by a black hole is thermal, meaning it carries essentially no information about what fell in. A black hole formed from the collapse of a star looks exactly the same, in terms of its Hawking radiation, as a black hole formed from the collapse of a giant collection of grand pianos. The radiation is perfectly random, as featureless as the glow of a heated poker. This created a paradox. Suppose you throw a book into a black hole. The book contains information, the arrangement of ink on paper, the specific words of the text, the molecular structure of the pages. All of that information crosses the event horizon and, presumably, falls toward the singularity. Now, the black hole slowly evaporates via Hawking radiation, but the radiation carries no information about the book. When the black hole has fully evaporated, the book's information appears to be gone, vanished from the universe. To appreciate why this matters so deeply, consider an analogy. Suppose you burn a book in a fireplace. The book is destroyed as a physical object, but in principle, the information it contained is not lost. The information has been transformed. It is encoded in the pattern of the ash, the precise temperature and wavelength distribution of the heat radiation, the arrangement of the smoke particles. If you had godlike powers of observation and computation, you could, in principle, analyze the products of the fire and reconstruct the original book, every word, every page, every letter. This is because the laws of physics governing the combustion process are reversible. They conserve information. Black hole evaporation, as described by Hawking's original calculation, is not like this. The Hawking radiation is thermal, meaning it is as random and featureless as the radiation from a heated rock. There is nothing in the radiation that encodes the specific details of what fell in. The information about the book is not transformed. It is gone, not hidden, not scrambled, gone. And this is a problem because one of the deepest principles of quantum mechanics is unitarity, the idea that information is never truly destroyed. Unitarity is not a minor technical requirement. It is the backbone of quantum mechanics. The entire mathematical structure of quantum theory depends on it. Without unitarity, probabilities do not add up to 1. Without probabilities adding up to 1, quantum mechanics ceases to make predictions. Without predictions, it ceases to be a theory of physics. Unitarity is not something you can casually discard. It is the load-bearing wall of the entire edifice. Hawking argued that black hole evaporation truly destroys information and that unitarity is violated. This was a radical claim, and it divided the physics community. Most particle physicists and string theorists rejected it, insisting that information must somehow be preserved. Most general relativists were willing to accept it, given the compelling nature of Hawking's calculation. The debate became one of the longest-running controversies in theoretical physics. It attracted some of the greatest minds of the late 20th and early 21st centuries, including Leonard Susskind, Gerard T. Hooft, Juan Meldacena, and many others. Various proposals were put forward. Black hole complementarity suggested that information was somehow stored at the event horizon while also falling into the interior, without creating a contradiction because no single observer could see both copies simultaneously. The firewall proposal, introduced in 2012 by Ahmed Al-Mahiri, Donald Merolf, Joseph Polchinski, and James Sully, argued that instead of a smooth passage through the event horizon, an infalling observer would hit a wall of ultra-high-energy particles, a firewall, at the moment of crossing. The holographic principle, inspired by the ADS/CFT correspondence discovered by Meldacena in 1997, suggested that the information inside a black hole is encoded on its two-dimensional boundary rather than in its three-dimensional interior. much like a hologram encodes a three-dimensional image on a two-dimensional surface. The debate raged for decades. In 1997, Hawking bet John Preskill an encyclopedia that information was truly lost in black hole evaporation. In 2004, Hawking famously conceded the bet, handing Preskill a baseball encyclopedia and publicly declaring that he believed information was not destroyed after all. But he offered no clear mechanism for how the information gets out. In recent years, physicists have made dramatic progress on this problem. A series of breakthrough calculations, published around 2019 and 2020 by researchers including Netta Engelhardt, Ahmed Elmhiri, Jeffrey Pennington, and others, showed that by carefully applying the tools of semi-classical gravity, the information contained in a black hole is released in its Hawking radiation. The key discovery was that of quantum extremal surfaces, geometric structures that arise in the gravitational path integral and modify the calculation of entanglement entropy in a way that reproduces the Page curve, the specific pattern of information release predicted by Don Page in 1993 for a unitary evaporation process. The result was widely celebrated as a near resolution of the information paradox. Information does escape from black holes. Unitarity is preserved, but many questions remain. The calculations rely on mathematical techniques that are not fully understood. The precise mechanism by which information escapes, the detailed story of how a specific bit of data about a book thrown into a black hole eventually appears in the Hawking radiation, is still unknown. And the singularity looms at the heart of the puzzle. Because as long as a singularity sits at the center of the black hole, a point where space-time itself ceases to be well-defined, it remains unclear where the information is stored, how it is processed, and how it gets out. The singularity is the dark heart of the information paradox, the place where the contradictions between general relativity and quantum mechanics are sharpest and most unresolved. Escaping infinity. How quantum gravity might erase singularities. If singularities are the places where general relativity breaks down, then the natural hope is that a deeper, more complete theory of gravity will resolve them. A theory that incorporates both the geometric insights of general relativity and the quantum principles that govern the subatomic world. A theory of quantum gravity. We do not have such a theory yet. Despite more than half a century of effort by thousands of brilliant physicists, a complete and experimentally confirmed theory of quantum gravity remains one of the great unfulfilled promises of theoretical physics. But we have candidates, and several of them offer tantalizing hints that singularities may not survive the transition from classical to quantum gravity. The most developed of these candidates is loop quantum gravity, a framework pioneered in the 1980s and 1990s by Abhay Ashtekar, Lee Smolin, Carlo Rovelli, and others. Loop quantum gravity attempts to quantize spacetime itself, treating the geometry of space not as a smooth continuum, but as a network of discrete, quantum mechanical structures called spin networks. In this picture, space is not infinitely divisible. At the smallest scales, on the order of the Planck length, roughly 1.6 times 10 to the minus 35 meters, space has a granular, atomic structure. Areas and volumes come in discrete chunks, much like the energy levels of an atom. This discreteness has profound implications for singularities. In classical general relativity, a singularity forms because gravity compresses matter to infinite density in zero volume. But if space itself has a minimum size, a quantum grain that cannot be shrunk below the Planck scale, then the compression cannot proceed to infinity. The density reaches a maximum, finite value, and then something else happens. In loop quantum cosmology, the symmetry-reduced version of loop quantum gravity applied to cosmological models, the Big Bang singularity is replaced by a big bounce. Instead of the universe emerging from a point of infinite density, it transitions from a previous contracting phase, bouncing when the density reaches the Planck density, roughly 10 to the 93 grams per cubic centimeter, and then expanding outward. The singularity is gone. The universe has a finite past, a definite minimum size, and a smooth transition from contraction to expansion. Rigorous numerical simulations have confirmed that this bounce is a robust feature of the theory, occurring regardless of the initial conditions of the universe. Loop quantum gravity also offers hope for resolving the singularities inside black holes, though this work is less developed. Preliminary calculations suggest that the singularity at the center of a black hole might be replaced by a region of extreme but finite curvature, possibly opening up into a new region of spacetime, like a baby universe forming inside the black hole. These ideas are speculative, but they are grounded in the mathematical framework of the theory. String theory, the other major candidate for a theory of quantum gravity, approaches the problem from a completely different direction. In string theory, the fundamental objects are not point particles, but tiny, one-dimensional strings of energy vibrating at different frequencies. These strings have a finite size, on the order of the Planck length, which provides a natural minimum length scale that prevents the kind of infinite compression that leads to singularities in classical gravity. One of the most striking proposals to emerge from string theory is the fuzzball conjecture, developed primarily by Samir Mather of Ohio State University beginning in the early 2000s. The fuzzball proposal replaces the classical picture of a black hole, a smooth event horizon surrounding a vacuum interior with a singularity at the center, with a completely different object, a tangled, fuzzy ball of string-theoretic matter that extends all the way to where the event horizon would be. In the fuzzball picture, there is no singularity. There is no event horizon in the traditional sense. The entire region that would classically be the interior of the black hole is instead filled with a complex quantum state of strings and branes, the higher dimensional objects that appear in string theory. The surface of the fuzzball is not smooth but fuzzy, more like the surface of a star than the sharp boundary of a classical black hole. Information about what falls in is stored in the vibrational states of the strings and is released as the fuzzball radiates, naturally resolving the information paradox. The fuzzball conjecture is controversial. Not all string theorists accept it, and there is no direct experimental evidence for it. But it has passed a number of important consistency checks, and it represents one of the most concrete proposals from string theory for what replaces the singularity inside a black hole. Nick Warner, a string theorist at the University of Southern California, has compared a fuzzball to a neutron star, an extra-dense state of matter that has no singularity, supported by the repulsive pressure of quantum strings rather than the degeneracy pressure of neutrons. Beyond loop quantum gravity and string theory, there are other approaches that address the singularity problem, each coming at the question from a different philosophical and mathematical direction. Asymptotic safety, an approach pioneered by Steven Weinberg in 1979, suggests that gravity might become well-behaved at high energies due to the existence of a non-trivial ultraviolet fixed point, a special mathematical structure in the renormalization group flow that prevents the coupling constants of the theory from diverging. The idea is that as you probe shorter and shorter distances, the effective strength of gravity does not increase without bound, as naive calculations suggest, but instead levels off and reaches a finite, fixed value. If asymptotic safety is correct, the quantum theory of gravity is self-consistent at all energy scales, and singularities do not form. The matter collapsing to form a black hole encounters a regime of quantum gravity where the effective gravitational attraction weakens or changes character, preventing the compression from proceeding to infinite density. Recent computational studies using lattice methods and functional renormalization group techniques have found encouraging evidence for the existence of the required fixed point, but a rigorous mathematical proof remains elusive. Causal set theory, developed by Raphael Sorkin and collaborators starting in the 1980s, takes perhaps the most radical approach of all. It proposes that space-time is fundamentally discrete, composed of a finite set of points, called events, with a causal ordering but no continuous geometry. The familiar smooth space-time of general relativity is an approximation, emerging at large scales from the underlying discrete structure, much as the smooth flow of water emerges from the collective behavior of individual molecules. In this framework, the very concept of a singularity, which requires infinite curvature in a continuous geometry, becomes meaningless. You cannot have infinite curvature if space-time is made of a countable number of discrete elements. The density of causal set elements might reach a maximum near the Planck scale, but it cannot diverge. Singularities, in causal set theory, are not resolved. They simply cannot be formulated in the first place. There is also the more recent approach of non-commutative geometry, in which the coordinates of spacetime do not commute at very small scales, meaning that you cannot simultaneously measure position in two different directions with arbitrary precision. This built-in fuzziness of spacetime introduces a natural minimum length scale and has been shown in several models to smooth out the singularities that plague classical general relativity. Each of these approaches is incomplete. Each faces significant technical challenges, and none has been confirmed by experiment. But they all share a common theme. Singularities are not features of the universe. They are features of an incomplete theory. When the full theory of quantum gravity is finally discovered, the infinities and breakdowns of classical general relativity will be resolved, just as the infinities in classical electromagnetism were resolved by quantum electrodynamics in the mid-20th century, and just as the ultraviolet catastrophe of classical thermodynamics was resolved by the birth of quantum mechanics itself. The Planck scale is where this resolution is expected to occur, at roughly 10 to the minus 35 meters in length and 10 to the minus 43 seconds in time. The Planck scale marks the boundary between the domain of classical physics and the terra incognita of quantum gravity. It is the scale at which the gravitational energy of a quantum fluctuation becomes comparable to the energy of the fluctuation itself. Below this scale, the smooth spacetime of Einstein's theory is expected to give way to something radically different: a seething quantum foam, a network of spin loops, a tangle of vibrating strings, or some other structure that our current mathematics can only dimly anticipate. We have never directly probed the Planck scale. It is roughly 10 trillion times smaller than the smallest distance currently accessible to our particle accelerators. But the hope is that indirect evidence, perhaps from the cosmic microwave background, from gravitational wave observations, or from some as yet unanticipated experiment, will eventually allow us to test these ideas. The fate of singularities hangs in the balance. The edge of understanding. What singularities tell us about reality? We have come a long way from Karl Schwarzschild's letter from the Russian front. Over the past century, the concept of the singularity has evolved from a mathematical curiosity into one of the central problems in all of physics. It has driven the development of new mathematical tools, inspired revolutionary theories, and forced physicists to confront some of the deepest questions about the nature of reality. What do singularities tell us? At the most basic level, they tell us that our current understanding of gravity is incomplete. General relativity is a triumph of human intellect, a theory of sublime beauty and extraordinary predictive power. It has given us black holes, gravitational waves, the expanding universe, the bending of light by mass, the warping of time by gravity. Every prediction it has made has been confirmed by observation, but it contains within itself the seeds of its own limitation. The singularity theorems of Penrose and Hawking prove that the theory predicts conditions under which it ceases to be valid. It is as if you had a map that was perfectly accurate in every detail, except that at certain points it bore the inscription, "Here be dragons." The map cannot help you beyond this point. Singularities are where general relativity meets quantum mechanics in a head-on collision. At the singularity, the curvature of space-time becomes so extreme that quantum effects can no longer be ignored. But general relativity is a classical theory. It does not speak the language of quantum mechanics. And so at the singularity, two of the most successful theories in the history of physics stand face to face, each speaking a different language, each unable to translate the other's insights. The resolution of this impasse, the construction of a theory that speaks both languages, is the holy grail of theoretical physics. And yet, even without a complete theory, the observational evidence is becoming increasingly precise, tightening the constraints on what singularities can and cannot be. In April 2019, the Event Horizon Telescope collaboration released an image that immediately entered the canon of iconic scientific photographs. It showed a bright ring of superheated gas surrounding a dark central shadow, the unmistakable silhouette of the supermassive black hole at the center of the galaxy Messier 87, some 55 million light-years from Earth. The black hole, designated M87 star, has a mass of roughly 6.5 billion suns. Its event horizon is larger than our entire solar system, and the dark shadow in the image corresponds to the region from which no light can escape, the gravitational footprint of the event horizon on the sky. In 2022, the Event Horizon Telescope followed up with an image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. This image was even more technically challenging to produce, because Sagittarius A star is much smaller and more variable than M87 star. The hot gas around it orbits in minutes rather than days, meaning the image changes significantly during a single observation. The team had to develop entirely new computational techniques to produce a stable image from rapidly fluctuating data. While the Event Horizon Telescope cannot image the singularity itself, which is hidden behind the event horizon, it can probe the geometry of space-time in the immediate vicinity of the horizon, testing general relativity in the most extreme conditions ever accessed. So far, the observations are consistent with the predictions of general relativity for a Kerr black hole. The size of the shadow, its shape, and the brightness distribution of the surrounding ring all match the theoretical expectations. But the precision is improving with every observation and next-generation extensions of the Event Horizon Telescope, including plans for a space-based component that would dramatically sharpen the resolution, may begin to reveal deviations from classical predictions. Gravitational wave astronomy, which began with LIGO's first detection in September 2015 of the merger of two stellar mass black holes, has opened an entirely different window onto the physics of singularities. When two black holes spiral together and merge, they produce a burst of gravitational waves, ripples in space-time that propagate outward at the speed of light. The shape of these waves encodes detailed information about the space-time geometry of the merging objects. By analyzing the waveform, physicists can determine the masses, spins, and orbital parameters of the black holes with remarkable precision. And they can test whether the final merged object, which rings down like a struck bell in the aftermath of the collision, has the properties predicted by the Kerr metric. So far, the results have been spectacularly consistent with general relativity. More than 90 black hole mergers have been detected as of 2024, and every one of them matches the theoretical predictions. But the sensitivity of current detectors is limited. The subtle deviations from classical predictions that might signal the presence of quantum gravitational effects near the singularity are expected to be tiny, far below the noise floor of LIGO and Virgo. Future gravitational wave observatories will change this. The space-based LISA mission, planned for launch in the mid-2030s, will detect gravitational waves at much lower frequencies than ground-based detectors, opening up an entirely new band of the gravitational wave spectrum. LISA will be sensitive to the mergers of supermassive black holes and to the spiraling of compact objects into them, a process known as an extreme mass ratio inspiral. These inspirals are particularly valuable because the smaller object orbits the larger one many thousands of times before plunging in, mapping out the space-time geometry with exquisite precision. Any deviation from the Kerr metric, any hint that the interior structure of the black hole is different from what general relativity predicts, would show up as a systematic drift in the gravitational waveform over the course of the inspiral. And there are more speculative possibilities. Some physicists have suggested that quantum gravitational effects near the would-be singularity might produce observable signatures in the gravitational wave signal, subtle echoes, that would betray the presence of structure where classical theory predicts only a vacuum. The idea is that if the singularity is replaced by some quantum object, a fuzzball, a Planck star, a bouncing core, then the surface of that object might partially reflect gravitational waves that fall inward after a merger. These reflections would produce faint repetitions of the original signal, arriving at the detector fractions of a second after the main burst. Several groups have claimed tentative detections of such echoes in existing LIGO data, but the results are controversial, and the statistical significance is not yet compelling. If confirmed, however, gravitational wave echoes would be the first direct observational evidence that singularities do not exist inside black holes, and that they have been replaced by something finite and physical. The philosophical implications of singularities are as profound as the physical ones. If singularities are real, if they are actual features of the universe rather than artifacts of an incomplete theory, then the universe contains places where the very concept of physical law breaks down. There are regions where no equation can describe what happens, no prediction can be made, no measurement can be performed. This challenges the deepest assumption of science, that the universe is, in principle, completely knowable. If singularities exist, the universe has kept some secrets for itself, locked behind horizons and compressed into dimensionless points where knowing and unknowing become indistinguishable. There is a curious parallel here to the limits of knowledge in other fields. Kurt Gödel's incompleteness theorems, published in 1931, showed that any sufficiently powerful mathematical system contains statements that are true but cannot be proven within the system. Alan Turing's halting problem, formulated in 1936, showed that there is no general algorithm that can determine whether an arbitrary computer program will eventually halt or run forever. In both cases, the system in question is powerful enough to identify its own limitations, but not powerful enough to transcend them. Singularities in general relativity have a similar flavor. The theory is powerful enough to predict the conditions under which it breaks down, but not powerful enough to tell us what replaces it. Each of these results, in its own domain, tells us that there are walls built into the structure of knowledge itself. The question is whether the wall at the singularity is fundamental, or whether it is merely the edge of a particular map that will be superseded by a better one. But if singularities are not real, if they are resolved by quantum gravity into finite, comprehensible physical structures, then the universe is even more wondrous than we thought. The infinite densities and zero volumes were never really there. The breakdown was always in our theories, not in reality. And the resolution of the singularity problem will mark one of the great triumphs of human understanding, a moment when we finally pushed through the apparent limits of knowledge and found that, even in the most extreme environments the cosmos has to offer, the laws of physics hold. We are not there yet. The theory of quantum gravity remains incomplete. The interior of a black hole remains beyond our direct observation. The Planck scale remains beyond our experimental reach. But the progress of the past century gives reason for optimism. From Schwarzschild's solution in the trenches to Penrose's theorem in his London office to Hawking's radiation in his Cambridge wheelchair to the fuzzball conjectures and quantum bounce calculations of the 21st century, the story of singularities is a story of minds refusing to accept "here be dragons" as a final answer. Consider the arc of the story. In 1916, Schwarzschild found a singularity in the equations, and nobody believed it was real. In 1939, Oppenheimer showed that gravitational collapse could produce one, and the world went to war. In 1965, Penrose proved singularities were inevitable, and Hawking extended the result to the birth of the cosmos itself. In 1974, Hawking showed that black holes evaporate, creating a paradox that would consume theoretical physics for half a century. In the 2000s and 2010s, loop quantum gravity and string theory began offering concrete, calculable alternatives to the classical singularity. And in 2019, the first image of a black hole's shadow brought the physics of event horizons and extreme spacetime curvature from the realm of theory into the realm of observation. Each generation of physicists has pushed the boundary a little further, turned the unknown into the merely uncertain, and converted the mysterious into the investigable. The singularity, that point where space, time, and reality break down, may yet reveal itself to be not the end of understanding, but the beginning of something deeper. Somewhere out there, 26,000 light-years away, at the heart of our galaxy, there is a black hole. It is spinning. It is massive. And according to our best theory of gravity, at its very center, there is a place where the curvature of space-time is infinite, where the density of matter is infinite, where the equations that describe the universe produce only silence. Or perhaps there is something else there entirely. Something our equations have not yet learned to describe. Something that, when we finally understand it, will reshape our picture of reality in ways we cannot yet imagine. The singularity is not just a place where physics breaks down. It is a place where physics is waiting to be born. You have been watching the entire history of the universe. Do not forget to like and subscribe and leave us a comment to tell us what you think. Thanks for watching, and we will see you next time.